Jason? Hi, Jason. Hi, Jason. Okay, so we're going to be talking about the Raleigh's theorem homework, and in particular, I want to take a look at number 3. Sorry, wrong angle. -6 to -2. And so we have to determine, first of all, does f of -6 equal f of -2? And the answer is yes. And next we have to determine, is f continuous? On -6 to -2. Now, watch carefully what we're asking. If I look at a number line of values from -6 to -2, this question is asking whether f is continuous for every single value of x between -6 and -2, not just at the endpoints. So I actually need to check that f is continuous. Under most circumstances, a graph will do just fine. And if I look at a graph, I can see that f is continuous at every x between -6 and -2. So that's fine. If you needed to provide analysis to back that up, then you would use the limit definition. You would say that the limit as x goes to c of the absolute value of x plus 4 is the same as the absolute value of c plus 4, which is the same as f of c. So f is continuous for every single value of c in -6 to -2. Now we ask the question, is f differentiable on the interval -6 to -2? So we generate a derivative. And what we're really asking is, does this derivative have a value for every x between -6 and -4, not including -6 and -4, because we're talking about an open interval. So I'm talking about all of the values of x that are between -6 and -2. Clara, in particular, what you did was you evaluated the derivative at -6 and evaluated at -2 and said, yes. That's exactly the wrong question. I don't care about the endpoints. I care about all of these individually. So how do you do that? Well, take a look and just ask, does this function have any x's that are outside of domain, excluding values? Yeah, at x equals -4. F prime of -4 does not exist. And -4 is right smack in the middle of the interval that I'm looking at. And because there is one x value for which f prime does not exist, therefore f is not differentiable on -6 to -2, and so Raleigh's theorem does not apply. And that's it. Okay, are there any questions from last night's homework?
Number 7.
Number 7. And what function is number 7?
F of x equals sin x greater than equal to 0 less than pi over 2. We have a sin x.
I think I remember this one. And so we have an interval that we're interested in. What is your question exactly? Well, let's start with the problem. The problem says, does the mean value theorem apply? And if so, find C. Okay. So let's do a little bit of review. To determine if the mean value theorem applies, what conditions do I need to check? Okay, give me the specific condition in terms of this problem. If f is continuous on 0 to pi. Okay, so let's check that. Now when we're checking this, you want to think of the entire interval of numbers from 0 to pi. We observe that my function comes in two pieces. And the first piece has a domain of 0 to pi over 2, and the second piece has a domain in pi over 2 to pi. So I really need to consider three different questions. The first question I have to consider is the first piece continuous on 0 to pi over 2? Let's check that really fast. Cosine x, is that a continuous function? Yeah, think about the graph, it's continuous. So we are continuous in this portion of the domain. Now we need to consider the second piece, also continuous on its portion of the domain. Now we need to consider the joint, where the two pieces come together at pi over 2. Is my function continuous at pi over 2? And for that, we need to check the limit definition. Is it true that the limit as x goes to pi over 2 of f of x is the same as f of pi over 2? Well, let's find out. First of all, what is f of pi over 2? Cosine pi over 2 is 0, but f of pi over 2 is not 0.
So sine pi over 2 is 1,
Yes.
which is bigger.
Very, very sloppy. You gotta clean it up. Answer my question. What is f of pi over 2?
Pi over 2 is sine pi over 2.
Why is it sine and not cosine?
Because the domain.
Yes, we want to find the value of f when x is pi over 2, and that's sine of pi over 2. So this guy's wrong. Okay? Now what about the limit? The limit is going to require looking at limits from left and right separately, because the function has different definitions to the left and to the right of pi over 2. So I consider the limit as x goes to the pi over 2 from the left of that appropriate piece, and I consider the limit as x goes to pi over 2 from the right of that appropriate piece. And I observe that these two limits are different. And because they are different, the overall limit fails to exist. And because the overall limit fails to exist, we say that f is not continuous at x equals pi over 2. And because f is not continuous at x equals pi over 2, the mean value theorem does not apply. And that's it. Is that better? What did you learn? Better understanding of the domain. Yeah, I think you were confused about the difference between the domain and just the endpoints. And I think you're better now. Yeah. Okay. Any other questions? Another one? What's it? What's it say?
Basically, so like
the story you're talking about here.
Yeah, the car,
Yeah, it is actually.
the car that goes 159 miles for 2 hours,
Uh-huh.
and the commute is only 65. So you need to show that the car has been speeding up during this period.
Okay, good. And this is kind of a tie-in to today's lesson anyway. We're going to be talking about how do we use the mean value theorem. And if you look at the conclusion of the mean value theorem, which is that there is a C in a B such that f prime of C equals f of B minus f of A over B minus A, then what the mean value theorem is going to do for us is it's going to allow us to compute one of these two sides and use that to get information about the other side. And so in particular here, we have a car that goes 159 miles in 2 hours. I can immediately calculate its change in distance over change in time as almost 80 miles per hour. As almost 89 miles per hour. And now, because the distance that it travels is continuous, because the car cannot teleport, and differentiable, because the car has a definite speed at every time, therefore the mean value theorem applies to it, and because the mean value theorem applies, I can say that the car's instantaneous speed had to equal 80 miles per hour at some time t. So watch the logic. We have a well-behaved function, so we compute the average rate of change, and we say therefore the instantaneous rate of change had to be that amount at some time, not for every time, but at least one time. So my car was speeding at least once. Does that help? Okay. Well, let's get into our lesson. Basically, what we'd like to do today is say, why do we care about the mean value theorem? And we have two related ways in which we are going to care about the mean value theorem. To get there, let's go back and do some review. And the first bit of review that I want to do is to review our existence theorems that we have had so far. And the first one that we talked about was the intermediate value theorem. Or the IVT. If f is continuous, on the closed interval a to b, then f takes on every value between f of a and f of b. And so the picture that we have for the intermediate value theorem is that you have a function that is continuous on a closed bounded interval, and if I pick any value that is between f of a and f of b, let me call that value L, then I am guaranteed that my function f will intersect y equals L at least once. And our intermediate value theorem was really, for us, a kind of zero guarantor. It guaranteed us that if we had a function that was continuous and on a closed interval a b, and f of a was positive and f of b was negative, then f had to have a zero in between. Or vice versa, f of a was negative and f of b was positive. So we used the intermediate value theorem really to establish the existence of zeros. Our second was the extreme value theorem. If f is continuous on A to B, then f has an absolute max and an absolute min on A to B. And the picture here is that we have a function that is continuous between A and B. And so it has to have a max and it has to have a min value. And maybe that max is at a critical point, or maybe it's at an end point. Maybe that min is at a critical point, or maybe it's at an end point. But it has an absolute max and an absolute min on the closed bounded interval. So this theorem was an extremum guarantor. It guaranteed that we had extreme values. And finally, our third theorem was the mean value theorem that you have been working with. And you guys are familiar with the conditions. Go ahead and give them to me, everybody out loud. If f is
Continuous.
That's Tony. Where's everybody? If f is
Continuous on the interval A.
and
And differential equation of the open interval A.
then
There is a
where is that C?
between A and B.
Open or closed?
Open.
Open. Okay. Such that if you know the picture, it'll help you remember the formula.
What's that pharmacy equals after
Okay. The picture is that your tangent line is parallel to your secant line. They have the same slopes. And so this is a guarantor of tangent parallel to secant. And we could add a fourth one, Raleigh's theorem, onto this, which is a horizontal tangent guarantor. But the thing about Raleigh's theorem is that the mean value theorem encompasses it. So if f of A equals f of B, the slope is 0 automatically. So I prefer to just think of it as mean value theorem with Raleigh's theorem as a special case. So we have our 1, 2, 3 existence theorems. By the end of the year, we'll have 4. One about average values. Now, with all of that in place, I want to talk about two different applications. Use number 1 of the mean value theorem is in scientific analysis. And the speeding car problem that we just talked about is a good example of that. But I'm going to give you my own problem that we're going to make up numbers for. That is going to come from the realm of chemistry. Who's in AP Chem or okay. Yep. Have you had chemistry already? What? Have you had chemistry already? Yeah. Okay. All right. So you'll appreciate this. So suppose I carry out an experiment. And in my experiment, I'm going to measure the concentration of a compound in moles per liter. as a function of time in seconds. So time goes by, I carry out these measurements, and the measurements that I get, concentrations in moles per liter, are 0.450, 0.468, 0.512, 516, let's see here, 585, and 0.632. So those are my measurements. Now I want to ask you a question that you already know how to find. Estimate C prime of 1 and interpret in English in the context of this problem. Estimate C prime of 1 and interpret in the context of this problem. Go. Hopefully your computation looks something like this. Hopefully you went to either side of t equals 1 and found the values here. Like so. You get 516 minus 450 moles per liter. Notice that the units can be pulled right from the chart there. Over 2 minus 0 seconds. And that gives me 0.066, so 0.033. You can write that as moles per liter per second, or moles per liter second if you want to split it out. Now, how do I interpret this result in the context of the problem? We're going to say, first of all, what does C represent? Concentration. So we're going to say the concentration is increasing. Good. Perfect. Exactly right. Notice that this has 3 elements that are necessary. First of all, a word increasing or decreasing that shows that my concentration is going up. Second of all, a specific rate. And third, at a specific time. Those are the 3 necessary elements for my estimation. Very good. Now, all of this is just computations that we know and love. Now comes our mean value theorem question. Does this number have any actual relationship to C prime of 1? You see, I computed this as an average rate of change over the interval 0 to 2. That's not the question that was asked. The question that was asked is what is C prime of 1? And so what I did was I made this computation right here as an estimate for that value. But is there any relationship between the two? Is there any validity to this? The mean value theorem says yes. If C is continuous and differentiable, which is a reasonable assumption, then there is a T. I'm going to use the symbol T instead of C because C is for concentration here. Somewhere between 0 to 2, such that C prime of T is equal to that average rate of change, 0.033. So in other words, maybe C prime of 1 isn't exactly 0.033, but C prime of something close to 1 is. So this is the first use for our mean value theorem. In a scientific context, I can never compute a derivative exactly. But I can compute average rates of change all day long. And what the mean value theorem does for me is to tell me that my average rates of change, like this one right here, are related to my instantaneous rates of change as long as my function is well behaved, continuous and differentiable. Does that make sense? So this is the first major use. We take an average rate of change that we can compute, and we use it to say something about an instantaneous rate of change. So we do this all the time in scientific contexts. Let's take a look at the opposite approach. Now I want to take a look at an application where we take the instantaneous rate of change and use it to say something about average rates of change. Use number 2. To prove theorems. You guys remember a theorem that we used starting in December, the sine of f prime theorem. Remember that theorem? If f prime is positive on A to B, then f is increasing, right? Now, when we did this theorem in December, I stated it, drew some pictures, waved my hands and said, isn't this reasonable, that if f prime is positive, then that has to be increasing? And all of you nodded your heads and said, uh-huh. And with justification, because it was intuitive that if a function has a positive rate of change, then it should be going up, right? Makes sense. But we didn't really have a proof for it at the time. So we're going to have a proof at this time. So first of all, let us examine what does it mean for f to be increasing on the interval a to b. So let's draw a function that is increasing, maybe this function, and ask what does it mean to say that it is increasing? Well, here's what it means. It means that if I start at any point C and I go to the right to any point D, I must also go up. To be increasing means that if D is bigger than C, then f of D is also bigger than f of C. Does everybody see that this is a good basic definition of increasing? Another way of putting that is to say that for any D and C, the average rate of change is positive, because if I divide two positive quantities, I get a positive value. Okay, So you can sort of see where we're going with this, because what I am trying to do with my sine of f prime theorem is I'm trying to take something about the instantaneous rate of change f prime, and I'm trying to make it say something about the average rate of change f of d minus f of c over d minus c. So how do I do that? All right, well, here's our proof. Suppose that f prime is greater than 0 on the entire interval a to b. Now, pick any two points C and D in A to B such that D is bigger than C. I think you all agree that I can do that. Now, does the mean value theorem apply to f on the interval C to D? Well, because f prime is positive, therefore f is differentiable on the entire interval A to B, which includes the closed interval C to D. So f is differentiable on the closed interval C to D, so it is also continuous. So the mean value theorem applies to f on the interval C to D. And that means there is a t somewhere in C to D such that f prime of t is equal to the average rate of change f of d minus f of c over d minus c. But now, I don't know where t is. Looking at my graph, it looks like it's about right here, because what I'm doing is saying that there's a tangent line that is parallel to the secant line, right? So it looks like t is right about there. I don't know where this t is, but I know something about the sign of its slope. It has to be positive, because that was our supposition, that f prime is positive. And since f prime is positive, therefore the average rate of change must also be positive. And if the average rate of change is positive for all C and D, then f is necessarily increasing. The entire interval.
So, in order to make f prime of t greater than 0, like,
That was actually our hypothesis. That's where we started.
you can see like f prime of d minus f prime of c be negative and
No, careful. Not f prime of d minus f
no,
of
f
d.
of d, f of d minus f of c be negative and d minus c be negative.
Well, I chose d to be bigger than c so that that wouldn't happen. But I could, if I switched the labels, then that would be true. Yeah. Yeah. So what did we do here with this proof? Very, very interesting. We knew a fact about f prime, and we used that to extrapolate to a fact about the average rates of change. So our mean value theorem can go both ways. We can compute an average rate of change, like we did with our scientific example, and use that to say something about f prime. Or we can start with information about f prime and use that to say something about the average rate. Does that make sense? Because we have a little bit of time, I'm going to do a sneak preview of part of tomorrow's lesson. Here's the question that we want to answer tomorrow. Suppose I've got two different functions that have the same derivative. Do they have to be the same function? I'll let you think about that, but here's going to be our first building block for that for tomorrow. So here's a new theorem. If f prime is 0 on an entire interval a to b, I'd like for you guys to try to draw yourself such a function. Pick an A, pick a B, and try to draw a function that has a derivative of 0 for the entire interval. As I try to draw my function, I find that the only way that I can draw it is to draw it straight across. Which implies that my function is what type of function? More than that, it is linear, but specifically, it's constant, yeah. So that's my claim. If f prime is 0, then f is constant. Now, how does the proof go? First of all, it should be obvious that the converse is trivially true. If f is constant, then its derivative is 0. That's our constant rule. But that has no logical bearing on this question. Maybe there's some other function out there that also has a 0 derivative. Maybe. What we aim to show is, no, that's not possible. The only way that you can have a 0 derivative is to be constant. Now, why? Let's do it like this. Let's suppose that f prime is equal to 0 on a to b, and choose some c and some d Now, since f is differentiable on the closed interval a to b, therefore it is also continuous, and so the mean value theorem applies. So we can say, by the mean value theorem, there is a t somewhere in between c and d, such that f prime of t is equal to f of b, f of d minus f of c over d minus c. So there goes our mean value theorem one more time. But now I know something about f prime of t. It's 0. That's right. And I also know something about fractions. I know that a fraction can only be 0 if the numerator is 0. So that f of d minus f of c has to be 0, so that f of d has to be equal to f of c. Look at what that's saying. That's saying that the values of f of c and f of d have to be the same for any pair of c and d along the interval a to b. In other words, my function must be constant. Here's another way to see the same thing. Suppose my function wasn't constant. If my function was not constant, then there would be at least one point of bump above or below my function. And the average rate of change would be non-zero, which means that somewhere in here, my instantaneous rate of change f prime would have to be non-zero also. And it's not. So that's another way of seeing that same proof. So we'll call this the no bump theorem. Functions that have a 0 derivative cannot have bumps. Now tomorrow we're going to leverage this theorem to show something really important about functions that have the same derivative. But I'll leave that till tomorrow. Questions or thoughts?
Kind of like a Raleigh's theorem.
There are some similarities to Raleigh's theorem, yes. But it's really the converse in some ways. Raleigh's theorem tells me that if my function is fixed on the two ends, I can find a 0 somewhere in the middle for the derivative. Yeah.
f of c equals to f of b, why it's constant?
Oh, a constant function is one that does not change. So f of c equals f of d for every single c and d in the interval a3. Yeah. Remember that I chose c and d very generally out of the interval a3. Okay.